here's a problem about your heart and your brain, and you can decide which one is more important. So it's about pumping a fluid, which is blood, from your heart. I believe this is the anatomical drawing of a heart. From there up to your brain. And then there's like a thing on the side there. There we go. Heart to brain. Pumping it up in the air. And the blood has to have some pressure. You have to think about the blood pressure and the flow velocity. So here we go. Your heart pumps blood at 100 millimeters of mercury. So that is a pressure unit, remember. So it gives you some pressure at the heart and a flow velocity at the heart, 60 centimeters per second. Then at your brain, the capillaries have such a large area that the velocity drops to 0.7 millimeters per second. So you may think I thought capillaries were teeny things, but there's millions of them. So the point is the total cross-sectional area goes up by a lot because the flow divides into lots of little capillaries, so much that it slows down to here. So that's really doing the continuity part for you. Instead of giving you the areas and making you calculate it, we just told you that here you have a small area, you're at 60 centimeters per second. Here you have a huge area, it's all the way down to 0.7 millimeters per second. But the question is asking, how long could your neck be so that blood just reaches your brain without thinking about viscosity? And then we'll do a second part, same question, but let's say viscosity requires you to have some pressure in the brain, 80 millimeters of mercury. Okay, so we're treating this fairly approximately, but let's go ahead and think through what we get here. So blood is flowing. This is a flow problem. So let's see. So we have the heart here. We'll do H and B for our subscripts. And we're just going to apply Bernoulli formula because we have this quantity, this expression. It must be constant anywhere in the flow. And what is it? It's the pressure at the heart plus the height at the heart plus 1/2 rho v squared at the heart equals the pressure in the brain plus the height term in the brain plus 1/2 rho v at the brain squared. This is how all the flow problems work. So the trick is figuring out what to put in all of these. Let's see. So I'm going to take a little shortcut and tell you that if there's atmosphere applied in your heart, it's also applied in your brain. Okay, so let's just think about the actual little gauge pressures inside the body. There'll be a P atmosphere on both sides, say. So that'll just cancel out. I've been writing that down for most of these solutions. I just won't even write it down this time. Okay, so the pressure at the heart, you were told, is 100 millimeters of mercury. But we like to do things in MKS units. So the quick way to convert that is just to write it as a ratio of atmospheric pressure. That's how I usually actually convert these. I don't memorize the conversion factor. I just say the pressure in the heart is 100 over 760. That's an atmosphere times 101,325. So that's the pressure in the heart converted from millimeters of mercury to pascals. Okay, plus the density of blood. I don't think we said in the problem, but it's 1,000. Say it's the same as water. Need to add that to the problem. Let's see. So 1,000, 9.8, and then what is this H? The height of the heart. We're asked how long can the neck be, so we're going to just define that as 0 in our y, our vertical coordinate system here. So we'll put the heart at 0. 0 plus 1/2 1,000 is the density, and then we do have the velocity here, 60 centimeters, 0.6 squared. All right, so there's your three terms: pressure, height, or potential, and kinetic part. And that needs to equal the pressure in the brain plus this. So in this problem, what pressure do we need in the brain? And that's where it says, how long could your neck be so that your blood just gets there? So that means is it gets there with no pressure, or with no gauge pressure, maybe atmosphere, but it there's just nothing left to push it up. So this is actually going to be 0. And under it, I'll put in parentheses, just is the key word that tells me that that's 0. Just any higher and it wouldn't even make it is the idea. Not a very physical situation, but still, the answer will make it clear why. plus the rho GH for the brain. Well, it's 1,000 times 9.8 times H. This is what we're looking for. That's the length of the neck. That's the H with no subscript, right? So here it is. We were asked how long could the neck be. Okay, there's some chest in there, but you get the idea. And let's see, so that's our unknown we're looking for, plus, what about this one? 1/2,000 times in meters per second. What is that one? 0.0007 squared. All right. So if we look at all this, we actually can just solve it straight for h. Right? I mean, this term's actually 0 because the height is 0. Another term that's essentially 0, if you're doing this and don't want to make a calculator error, is this. If we look at these two terms, these are just numbers, and this one has 0.6 squared, and this one has 0.0007 squared. Okay, so this will be extremely small compared to this, since they have the same 1,000 and the same half. So essentially, it's just this term and this term, and this term. But since these, you know, are going to be the same here, 1/2,000, because that is so small compared to that, you can actually just ignore that if you want. Or if you want to calculate it and add it in, that's okay too. Okay? So if you go through this whole thing here, it's just 1, 2, 3, 4 terms with an h, you get that the h is 1.3 meters, I believe. Let me double check that. That's what I got. Yeah, 1.3 meters. So you say, well, that's a pretty long neck, isn't it? Right? 1.3 meter long neck, even if you include the brain heart. I mean, that would be a really, unusual baby giraffe level neck here. And the reason is we made this sort of ridiculous assumption that there's no viscosity in blood, which actually has significant viscosity. So, and also this ridiculous assumption that you would want to get blood to your brain with no pressure. I mean, even if you're not fighting viscosity, you need some pressure and keep your blood vessels from collapsing or something. So that's why we said, now let's do something a little more realistic and consider viscosity, but not the detail how to solve, viscosity problems in fluid mechanics, but just say because of viscosity, we want to get there with 80 millimeters of mercury. That's the pressure we want to get there with. So for that, everything is the same except here. We say, no, you got to get there with 80 over 760. Let me give myself some room here. 80 over 760 times 101,325. You get the idea. Put the pressure here, convert it to Pascal. And what that's going to do, that's going to come over here, make this term smaller. H will end up smaller. And if you do this, it's the exact same formulas in math, just with one more term, you get 0.29 meters. And that one is a lot more reasonable, right? 0.3 meters, okay, that's starting to sound on a human scale. And this even makes sense physiologically, right? 80 millimeters, that's sort of like when you measure your blood pressure, that lower number you want to be around, 60 to 80, something like that. And then the diastolic, or the systolic, the high one, 100, that's order of magnitude. So we used fairly realistic numbers, and we got a fairly realistic neck height here. So this was an example of Bernoulli equation where we had height difference, we had a flow rate difference, although one term was basically negligible. And we even had a pressure difference, so we're including all the terms in this problem.